Good morning, chemistry team. Welcome to video number 12 in our electrochemistry journey. Not quite getting to the end, but getting closer and closer. This is a long chapter. This is a key one. Not going to be a super long video, but this is a key one because we're now going to connect a lot of the stuff we've been doing for the last month and a half, 2 months. We've been doing thermodynamics. We've been doing equilibrium. It feels like it's been years, right? And now we're doing electrochemistry. It's time that we tied the knot with all three of them, right? We got Lancelot, King Arthur, and Guinevere. Let's put them all together in this triangle of doom. But see how we can connect these. So we're going to take electrochemistry and try to connect that to equilibrium. We've already connected electrochemistry to thermodynamics, right? And we've connected thermodynamics to equilibrium. Oh, maybe there's a trend here. Ho, 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 ho. So from thermodynamics, we found that the Gibbs energy change at standard conditions was equal to negative RT log K, the equilibrium constant, right? We also just found in the last video or two in electrochemistry that the Gibbs energy change at standard conditions is equal to negative Z, the electron number, times F, the Faraday constant, times the cell potential at standard conditions. Oh. But if this is somebody, right? Say this is, Tony, and that's Susie, but they don't know each other, but they both know Bob. And Bob goes, oh, Tony and Susie, they'd be a good fit together. So let me connect Tony and Susie together through Bob, and then we connect them together, and then Bob just disappears like a matchmaker. Oh, right? The friend of my friend is my friend. So if delta G naught is equal to this and this, therefore they must equal each other. Yay, algebra substitutions. So negative RT log K from thermodynamics must equal negative ZFE naught cell from electrochemistry. And now we have connected electrochemistry to equilibrium. The negative signs cancel out. Let's isolate E naught cell, divide both sides by negative ZF. So we end up with E naught cell is RT over ZF times log K. That's a key, one of the most important equations we're going to find in electrochemistry, because now we can take these standard electrode potentials, right, our friends there, calculate E naught cell, and from that we can determine equilibrium constants. Hey, nice stuff, right? R, of course, is the gas constant, 8.3145 joules per mole Kelvin. Temperature has to be in Kelvin, obviously, because R is in Kelvin, commonly at 25 degrees Celsius, but not always. Z is the electron number, unitless. That's the number of electrons transferred between the anode and the cathode. And F is Faraday's constant. What was that? 96,485 coulombs per mole, something akin to that. I'll give you all of those. Now, in the textbook, in a lot of places you'll see this collapsed into a shortcut, because so many times we do it at 25 degrees Celsius anyway. So if you put in 298.15 Kelvin for the temperature and just assume that's always that temperature, well, R is always the same, F is always the same. If the temperature is always 298.15 Kelvin, you can collapse RT and F into one term and just get E naught cell is that constant divided by Z times log K. I don't particularly care for that because too many times students use that and just assume that that's true for every temperature. No, that's only if it's at that temperature. Now, yes, we do most of our stuff at 25.0 degrees Celsius or 298.15 Kelvin. True, but what if I throw and you get so used to using that shortcut equation that I give you something at, say, 75 degrees Celsius, and you pop in the shortcut and you get it wrong because you did the temperature wrong. So not a huge fan of that. Yeah, it's great, but not a huge fan of it because I find too many students just assume and make it. And you know what happens when you make assumptions, right? So I'm only going to give you this equation on my quizzes and exams. I want you to understand the temperature dependence of it. Be very, very careful when you use shortcut equations. So what can we glean from this information? Obviously, we've got an example problem coming. Yay! If K is increasing, now we remember from equilibrium, the larger the value of K, products raised to the power of their stoichiometric coefficients over the reactants raised to the power of their stoichiometric coefficients, if they're in the gas phase or aqueous phase. Well, the bigger K is, the more products you have at equilibrium. The smaller K is, the more reactants you have at equilibrium. So if K gets bigger, right? If it's bigger than 1, obviously, this will be a positive term. These are all positive terms. So E naught cell will be positive if K is bigger than 1. And as K increases, E naught cell increases. And of course, so if K is bigger than 1, it's spontaneous towards products at equilibrium. So E naught cell will be greater than 0. And obviously, if K gets bigger, this is negative, delta G goes down. So delta G is opposite those two, right? Spontaneous in the forward direction has a negative delta G, a positive E cell. And if K is much, much bigger than 1, and you get to around the 10 to the 10th range, it's pretty much almost all products anyway. We would almost say that goes to completion. And 10 to the minus 10 on the opposite, if K is less than 1, this becomes a negative term, log of a number, right, less than 1. Less than 1 there would give us a negative E cell, which means non-spontaneous in the forward direction. Delta G naught would be positive, non-spontaneous in the forward direction. And the lower K is, the more reactant dominant it is. Oh, so many terms. What do I do? And if it's around 10 to the minus 10-ish, we would almost say no reaction occurs. But really weird. What's the log of 1? It's 0. So if K is equal to 1, the cell potential at standard conditions goes to 0. And Gibbs free energy change at standard conditions also goes to 0. Interesting. Not like that's ever going to probably happen, but hey, let me kind of put this in some graphics and then we'll do an example problem for you. Nice, quick, but important. All right, let's take all that stuff I was jibber-jabbering about and just stick it in a graph. People like pictorial views, right? So this is the Lancelot, King Arthur, Guinevere, love triangle here. We've got equilibrium, we've got electrochemistry, we've got thermodynamics. This is kind of like that pH square I drew seems like forever ago, where you got the pH, POH, H3O plus and OH minus. You can connect them as a square, but you can't go across the diagonal. Well, with a triangle here, we can go from any one to any other, which is wonderful. So from thermodynamics, right, that was the first one we did. We related that to equilibrium with delta G naught, negative RT log equilibrium constant. That's the first one we introduced. Then when we got to electrochemistry, we were able to connect that to thermodynamics. Delta G naught was negative ZF E naught cell. And now because those equal each other, right, we have E naught cell as RT over ZF log K. So we can take thermodynamic information, maybe from a thermodynamic table, calculate delta G naught at really any temperature. If it's at 25 degrees Celsius, we can go straight from the table. If it's not at 25 degrees Celsius, we got to do delta H, delta S, and delta G is delta H minus T delta S. And once we have that delta G, right, we could go to E naught cell or we could go to K. Okay. We could do the same thing. We could use these electrochemical tables here. Yes, the friends we've been dealing with for a while, and calculate E naught cell. And from there, we could go to the equilibrium constant or to delta G. Right? If we had an equilibrium constant, we could go to E naught cell or delta G. As long as you have laboratory data or theoretical information from any one of these, you can go any direction you want, my friend. Oh, I can think of so many questions I could throw at you for quizzes and tests. You'd better study. Let's do a problem like you might see that the evil professor would throw at you. All right, here, and there's several different ways I could ask you these types of questions. So here, determine the equilibrium constant, K, at 25.0 degrees Celsius. We've got our temperature. And standard conditions for the following. Now, I could give you an overall chemical equation, or I could give you line notation. Now, the reason I like the line notation here, because it implies that we're going to calculate the equilibrium constant from electrochemical tables. Right? So if I just gave you an overall equation, it doesn't really specify whether you're going to do this using thermodynamic tables to calculate delta G naught and then get K, or to use electrochemical tables and use the standard electrode potentials to calculate E naught cell and then get delta G naught. So you don't know which way to go. I'll either state that, use thermodynamic tables or use electrochemical tables, or I'll pick a reaction, an equation where the data, say, is on an electrochemical table, but not on a thermodynamic table, so you can find it on one but not on the other. But if you can find the values on both, then there's two ways you can do the problem. And I may have intended one way. I try not to make those mistakes. So because of the line notation, we got cell line notation. The hint there is you should do this with electrochemistry. I don't even need to stay at standard conditions because standard conditions are stated in the line notation. So if I didn't put the 1 molar there and it's just as standard conditions, that's fine. So it's kind of redundant to say standard conditions or write the 1 molar there. So let's glean from this what the reduction half reaction is, what the oxidation half reaction is, figure out our standard reduction potentials and for the cathode, and then do the same thing for the anode, reverse it and change the sign, add them together and get E naught cell. That'll be step 1, right? And get the overall equation, just like we've been doing over and over. What's the overall equation? What's Z? What's the electron number? Electrons being transferred from anode to cathode, and get E naught cell. Then we've got something new. Once we have E naught cell, we can calculate the equilibrium constant with our new equation. Ha ha ha! Not a big deal. So let's figure out, well, actually, you pause it and see if you can find on here, because I gave you the reactants and products. So see if you can find the half reactions on this table. Remember, the anode's going to be reversed from what it says on the table. Obviously, we always do the anode first, the oxidation. So this should be an easy one. You got silver solid going to silver +1. So the silver could actually be the electrode. We can bend that over a beaker and put an alligator clip on it. So that's that one, standard conditions. So the cathode, the reduction, must be this complex ion. What's that? Tetrachloro. Whoops. Negative sign goes on the outside. Humana, humana. Tetrachloroorate 3 ion. Been a while since we've done complex ions. We got to use the Latin root because it's negative. Tetrachloroorate 3 ion. Yeah, I think that's right. Somebody, if that's wrong, one of you guys are going to get me. So we're taking that as standard conditions, and then we're going to be forming chloride ion and solid gold. Solid gold. Oh, the solid gold dancers. I remember watching them when I grew up. And since gold, we could use that as the actual electrode in this case, although I'm pretty sure that would disappear quite readily in lab if we had gold electrodes. Right? Where'd all everybody's electrodes disappeared in lab again? So find that one. And remember, this will be the reverse of what you find on the table. Okay. See if you can find those for me and calculate, get the overall equation. Tell me what Z is. And then, so overall equation, Z, and E naught cell. See if you can do that for me. I'll go ahead and write that on the board. See who wins. How you doing so far, my friends? I ran out of board space. This is as far as I could get. Digging through the tables here, I was looking for the silver one. The silver one should be pretty easy for the oxidation. This one was kind of hard, so I poked around. I was going to say my goggles. I need my eyeballs. So if you look here, do you see the tetrachloroorate 3 there? Plus the 3 electrons going to solid gold plus 4 chlorides. You see that? And that's the 1.002 volts. That's the reduction half reaction. Boom. So I found that right there with the 1.002 volts. Boop-a-doo. There's our baby. That was the tough one. And again, if you're confused on the half reaction, just scan through it. So the more you use this, the more you recognize things. You don't want to waste a lot of time on a test going, oh my God, where is it? Remember, these are acidic solution. Then we've got some, we haven't done any yet in basic solution. So watch out for that on an exam or homework. It says, hey, in basic solution. Then you go, oh, bing, 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 boom. I can go to the shorter table right here because there's not as many showing up in basic solution there. All right, and it's hard to tell from here. I don't see H pluses, H0 pluses, or OH minuses anymore. Now the silver one is for the anode, so it's going to be backwards. So we'll find the Ag plus going to Ag solid on here, but we want the reverse of that. So let's look for the silver one. I'm always looking for silver. All right, can you see the Ag plus, silver plus 1 ion plus an electron going to solid silver, 0.800 volts? We need the reverse of this. So we need to flip that equation. Therefore, the anode cell potential is the negative of the 0.800 volts. So we got 1.002 volts for the cathode, right? The reduction half reaction. And then for the anode, it's the opposite. Since we flipped it, negative of that. Overall equation, notice there's 3 electrons, right? In the reduction half reaction being accepted, but only 1 produced in the oxidation. Those have to equate with each other. So I had to multiply the oxidation half reaction by 3, so that when I add these together, I get 1 of the tetrachloroaurate 3 ion, 3 electrons, plus 3 solid silvers. And on the right-hand side, I'll get 1 solid gold, 4 chloride ions, 3 silver plus 1 ions, and 3 electrons, and the 3 electrons cancel out. So here's my overall equation, which I could have given you instead of the line notation, but hey, why not get some extra practice going from one to the other, knowing how to read these line notations. So we're at 25.0 degrees Celsius. We need to add these two together to get E naught cell. I would love to have put that on this board, but I ran out of room, so I'll do it on the next one. And we should be able to get Z from this. Let's take a look. Right, 3 electrons collected at the cathode, 3 electrons released here. So I know that Z is equal to 3, my friends, because we're going to need that when we're going from the cell potential at standard conditions to the equilibrium constant, right? We need R, we need F, we need Z, we need T in Kelvin, all that fun stuff. So let me erase the board. Go ahead and add those two together. I know you can do that to 3 decimal places. And you should be able to use that equation I gave you that relates the standard cell potential to the equilibrium constant. You know Z, you know R, you know T, you know E naught cell, you know F. Go for it. Should be pretty easy from this point. Summarizing my information. E cathode plus E anode. So there's my cathode, 1.022 volts, straight off my reduction electrode tables. There's my anode, right? It's the negative of what was on here because we reversed it. Add them together, good to 3 decimal places, I get 0.202 volts at standard conditions, right? We still haven't looked at non-standard conditions. That'll be the next video. Yay! Go Nernst equation. We need the temperature in Kelvin. You don't have to show me that, but the problem is a lot of people screw up their significant figures when they skip steps and don't show it. We're at 25.0 degrees Celsius, which is 3 significant figures, but doesn't matter because we're adding this exact 273.15 to convert it to Kelvin. So we're limited to the tenths place. So it's 298.150 Kelvin, good to the tenths place, which gives us 4 significant figures. Oh, so it goes from 3 sig figs to 4 sig figs when we go from Celsius to Kelvin because we're using rules of the largest absolute uncertainty, or fewest decimal places. And of course, Z was 3. That's the number of electrons transferred between the anode and the cathode. So let's get our trusty dusty equation. Yay, equations. Let me use purple here. So we know that E naught cell, my naught looks like a dot there. E naught cell is RT over ZF log of K. That would be provided for you on like an equation constant table or a page or something like that. So let's solve for log of K first. Right? Let's rearrange this. Let's isolate log of K, solve for that, and then go E to that. Right? Because the inverse of the natural log is E to the X. So you hit the inverse function or second function key on your calculator, and then you can have at it. So let's rearrange this. So log of the equilibrium constant will be the standard cell potential times the electron number times Faraday's constant over RT. Oh, know your algebra, my friends. Let's plug in all of our information there. What was E naught cell? Let me push this down here. This is going to get a little squishy. E naught cell was 0.202 volts. You know what I'm going to do? I'm going to push it down here because this is going to extend over quite a bit. Let's put 0.202 volts. Now the volts aren't going to cancel anything out. You have to realize a volt is a joule per coulomb, right? So a volt is a joule per coulomb, or times coulomb to the -1 power. That allows me to cancel out volts, and then we need joules to cancel out joules in the value of R. We've got E cell. We need Z. What was Z? It was 3. Unitless numbers, the electron number. Faraday's constant, 96,485 coulombs per mole. So we've got coulombs in the numerator, and that's coulombs to the -1, so it's actually in the denominator. So inverse coulombs and coulombs cancel out, my friends. Remember, we're doing a log term, so all the units need to cancel out. Oh, if you have units left over, something's not right. let's divide by R. And in a unit line equation, right, when you divide by something, you just put the numerator on the bottom and the denominator on top. You flip it. So let's go 8.3145 joules per mole Kelvin. So when you're dividing by something, you just multiply by the inverse. Let's take a look at our units. We've got moles in the numerator, moles in the denominator, joules in the numerator, joules in the denominator. All I have left is Kelvin, so is it intuitively obvious to you? We have to divide by the temperature to cancel out the Kelvin. See, unit line equation, dimensional analysis rocks, baby. Let's divide by our temperature, which is right here. So we're going to have 1 over 298.150 Kelvin. Oop, that's pretty ugly there. Boy, even pushing it down, it's still got major squish factor there. I've got three significant figures in my voltage. That electron number is exact. Got way more than I need in my Faraday's constant, way more than I need in R, and I got 4 in my temperature, so I'm going to end up with 3 significant figures. I'll squish this on the bottom. You know what? Boy, I'm running out of room here. I have so much little to go. Maybe I'll push this into the center over here. All right. So let's get this value of log of K, and then we'll just solve for K right here so I can leave it up on the board rather than erasing it and doing a whole new board. The limitations of what I'm doing. All right. So go through and calculate that out real quick. Get your trusty dusty calculator to 3 Sig Figs. What do you end up with? 20, what do we Sig Figs? 3, so 23.586. 23.586. Good to 3 significant figures. Carry those non-significant. You can carry as many non-significant digits as you want, but they're not significant, so give me 2 or more. And so we only have one more step. I'm so close on my board. Let's do it in blue. So let's carry this over here. This is going to get messy. Whee! So K will be e to that power. 23.586. You know? So ideally, I just needed one more line here. I'm like, oh, I need a lower board. And I could write smaller, but then you couldn't see the board. Wonders of technology. You like my highly digital technology here? Hey, we do the best we can. So now I'm taking, so Sig Figs, the number of decimal places in the E function will give you the number of Sig Figs in your answer. So since we have 1 decimal place in our E term, we're going to have 1 significant figure in our value. Now that's an e to the positive number. That's going to give us a big value. So K is going to be a lot bigger than 1 in this scenario. So let's see what we get here. Good again to 1 Sig Fig. So 1.75 times 10 to the 10. 1.75. Good to 1 Sig Fig. And that's closer to 2, so we're going to round that. So that'll round to 2 times 10 to the 10th. So sorry for the squish factor in the middle there. That board looks like a mess, but if you follow in the sequence, we're good to go. So calculate log. So pretty much you look at the steps. Step 1, get the overall equation and E naught cell and Z all together. Step 2, plug it into this equation, solve for log of K, and then do E to that value. That is 10 to the 10th. So K is huge. That means this is going to be extraordinarily product favored at equilibrium. Right? So delta G naught would be negative, E cell is positive, K is big, good, and it's 10 to the 10th, so we could almost say this goes to completion. That's how you get K values, and we can reverse it and all that fun stuff. So make sure you do your homeworks. Yay, us!